Welcome to our science seminar today. It's our pleasure to have with us today Mohammad Omary from University of North Texas. Okay. And Dr. Omary is a very interesting guy. He grew up in Jordan. He has his bachelor's degree in chemistry and electrochemistry as a master's in that from Yarmouk University in Jordan. And then he has a PhD from the University of Maine. Okay. And he's been at UNT for a good long time now, what, 17 years? 17 years. And he's made quite a name for himself while at the University of North Texas over there. He is now a distinguished faculty, which is a title that they usually give for someone who's, ended their career and, sort of an honorary type of thing. But he's earned that title while he's in the middle of his career here. He had over 100-some peer-reviewed publications. He has grants totaling over $15 million, okay, mostly from the U.S. Department of Energy. He's worked with NASA, the state of Texas, and numerous other things. He has a National Science Foundation Young Investigator Award, which is a really hard thing to achieve. So Dr. Omary comes to us with lots of credentials today in the area of inorganic chemistry. And so he and one of our own, Claire, will be presenting today. And after seminar, we'll be having lunch in the Joyce Room. So if you have more questions or want to meet Dr. Omary and hear more of his story, his life story, and all that sort of stuff, you might want to come to join us for lunch. But until then, let's give a warm welcome to Dr. Omary.
Thank you all. Howdy. After my PhD, I did 2 years of postdoc at Texas A&M, so that's I'm a semi-Aggie, so to speak. I would like to share my journey about chemistry, how we progressed from pursuing basic science to add application to design materials that hopefully help improve our life in different areas of science and technology, even biomedical applications. So, but as you will see, the take-home message from this whole talk would be that we're using science to help improve the design of the material, so they're not mutually exclusive. I gave this lecture last April. We had this faculty lecture series. They changed the name to Smart Talks a little bit later. Trying to relate to the general audiences when we have our College of Science split from the College of Arts and Sciences, so they wanted to have their own colloquium series, and so I was speaking to a general audience of chemists, biologists, physicists, mathematicians, and even some lay people, and this is why it wasn't like heavy on basic concepts of chemistry. So you all should be able to follow different details. So what we wanted to do is look at different material design where we can address multiple issues. The first issue is energy. So when we talk about energy, we talk about an all-of-the-above approach. When you hear politicians talk about all-of-the-above approach regarding energy, they only focus on the source, being like fossil fuel versus wind, nuclear, solar, etc. Right? When I talk about all of the above for energy, I talk about not just the source, also the existing sources, whatever they are. We need to do better job in energy saving. So that is one area of what we do is energy saving, lighting and video displays. Then energy harvesting, that is where we do focus on solar in terms of looking at our research, but even existing technologies, both existing fossil-based as well as renewable sources, they both have advantages. have needs for energy storage. So you would need to store the solar energy. You also need to store gas phase fuels like hydrogen, which is a very clean energy source in fuel cells, or natural gas. So Texas and the U.S. are leading the world in natural gas production, but to use it more effectively, we need to worry about some environmental problem, but also need to store it in a solid phase so you can transport it and utilize it more easily. So we have work in all of these technologies, resulting in 6 patents, 2 on saving, 3 on storage, and 1 on harvesting so far. So the first application or app in today's millennial language is on energy saving. The Department of Energy invested in us about $2.3 million in 2007 for a 3-year project. And at the time, the challenge was trying to solve basic problems, applied research problems that hamper the widespread of LED lighting, solid-state lighting. So the issue, you can see, read the numbers there. So they made a 20-year projection from 2005 to 2025. They made this projection after that period started. So if we and the other people that they invested in solve the problems confronting the technology, they estimated that would lead to $120 billion saving, in addition to generating revenue more than $10 billion a year, etc. When they gave us this big money, us and 12 other teams, at least that was in my round, so these people started solving the problems even at a faster rate than what they had hoped, and even better accomplishments. So the next projection out more than doubled from 120 billion to 250 billion. And last year, it tripled, $630 billion. So basically that tells you that, give us, show us the money, and we will actually solve the problems. I'm talking about us, meaning not me personally, scientists, engineers, technology, the private sector. There is a lot of smart people out there. So if you invest in these issues, you will actually have this outcome. And you're talking about sky's the limit. So if you see, between lighting and displays, there's more than 30% of the energy consumption. So even with the first estimate, it is 30%. Now it's actually becoming less than 30% because 30% versus the old technology. But right now, the lighting aspect has been become more efficient. So its proportion of the proportion of the electricity dedicated to lighting would go a little bit lower. Okay, so if you look at the conventional light sources, and everybody and their sister have basically an incandescent lamp in their house, I think. Well, the incandescent lamp doesn't have any problem in terms of toxic materials or sustainability. We at UNT, we pride ourselves of being, we mean green is our motto, right? So each of these technologies actually still has sustainability issues. So as far as toxic materials are concerned, there's nothing wrong with the incandescent lamp. It's just a tungsten wire in there. But it's only 10% efficient, which means that 90% of the power consumption goes down the drains, goes up the atmosphere to produce tons of CO2. You can see the numbers, 4,500 pounds per year. So the CO2 emission is humongous. So basically you waste 90% of the power consumption from coal or whatever the source is. If you go to the next technology up, the compact fluorescent lamp, or the fluorescent lighting, whether linear fluorescent or the compact one that fluorescence that you see in the picture, you get the same light out of a 60-watt lamp with only 14 watts. So you save 4 times the energy. If you go to the LED, you actually save 6 times, and that is like in and the fixtures that are produced at large scale, where there is some variation in effectiveness. Indeed, LEDs, including the OLEDs that we make, they can save 90% of the electricity. So basically, they can be 100% efficient. So instead of 6 times, 10 times. So you can, the limit is 6 watts per, instead of 60 watts, 6 watts. Okay. So the problem is that both the fluorescent lighting and the LED lighting, they still have challenges. The fluorescent lighting uses mercury, and in the gas phase, so it is the only toxic form of mercury. When we were little kids, we were playing with mercury, right? We shouldn't. But anyway, but that's not to alarm you to, overtly, because, the amount of mercury is like 6 torrs, very small pressure. But you can imagine, in the place where it's produced, where the lamps are made, as well as when you dispose of them, if there's an accident, it can and it will kill people because the amount of mercury would be more significant than the individual lamp. So the mercury produced will only give you UV light. Mercury light emission will be in the UV. But to convert it to white light, they have to add to the glass, in addition to the white matrix, which is, aluminum, it's called barium, aluminum, something else in it. It's pretty cheap, but they dope small amounts of rare earth materials, rare earth ions. So typically, europium in the +3 oxidation state gives you a red, and in the +2 oxidation state gives you blue, whereas the green you get it from terbium in the +3 oxidation state. So the LEDs, they utilize gallium nitride, and that gives you blue light instead of UV light. So you only need the red and green from the rare earth phosphors, but you still need them nonetheless. So rare earths are rare from the name, right? But besides being rare, their mining is associated with an extremely heavy environmental cost. There's a lot of nasty stuff from the mines that produce rare earths. And one single mine in China is responsible for 45%, almost half the entire world production of it. So even in China itself, I've been in China 3 times so far, they have a lot of efforts right now to look for rare earth alternatives. So that is one alarming thing about that. But even more alarming, if you're looking for video displays as opposed to lamps, then you actually need the individual pixel of the red, green, and blue to be out of rare earths. And for that, the red pixels, the same pixels used not only in video displays, also in traffic lights. The red traffic lights, they contain gallium arsenide, so they have arsenic, the most toxic element in there. So there's a lot of issues that are associated with all of these different technologies, but because we're inorganic chemists, we can implement our "we mean green" argument, because basically we have the entire periodic table to play with. We can design it focusing on, if we must use metals, we can look for cheaper metals like copper as opposed to iridium or platinum or gold. If we need to use metal-free materials, we have the rest of the other periodic table. So we can choose the green color-coded elements here in the material design, and that makes our life a lot easier. So all the numbers that I showed you earlier about energy saving is only for lighting, but right now, we have all of these fancy gadgets that have become ubiquitous, right? Everybody has them, and if you replace those with better materials and better devices, then sky does literally become the limit. So all of those astronomical numbers will multiply even further, because the DOE projected them only based on LED lighting. not based on video displays at all. So we can see the amount of video display produced worldwide have increased dramatically. So ultimately, it will come down to the device thickness. If you have the same thickness between an LED and an OLED, an organic LED, if you can reduce the thickness by a certain factor, then ultimately, if you solve the other scientific problem, engineering problem, you will get more efficient lighting. So if you take the typical thickness of an LED display, it's in the millimeter scale, versus the DFWs, OLEDs, DFW, dopant-free white OLEDs, not that's for sure. So pun was intended in there. So those are in the nanoscale. These are the type of devices that Claire made in my lab last summer in her REU scholarship, and she will talk a little bit about some of the details in a minute. So the gradient in the thickness actually makes it, sky's the limit, 10 million %, 100,000 times more energy efficient. That is theory. That's why we have to do research in the lab. Because in real life, Samsung Galaxy product, which use OLED, they have only 40% efficient, more efficient light device efficiency than the iPhones up to the iPhone 10. iPhone up to iPhone 8, all of them use fluorescent lamp in the background, called cathode fluorescent lamp in the, as the light source, and then they have filters to give you the individual pixels, and the display itself, the electrical engineering of the display is based on still the same technology of the old calculator, the LCD. So there's a lot of room for improvement, yet the industry is quick to pumping more and more and more products, so we have up to the iPhone 10. The iPhone 10 finally uses the OLEDs. And by the way, this 40%, not 10 million %, 40% energy saving is only with a black background. So in a screen like this, in a background, in a slide like this, or most web pages, most PowerPoint presentations, Word document, whatever, if the background is white, actually the iPhone product is more energy saving than the Samsung Galaxy product. So there's a lot of room that we still need to reach, even a fraction of the limit that I identified here. So we do football-related research, of course, in Texas. So UNT is the proud partner of the Dallas Cowboys. The Cowboys Stadium, AT&T Stadium, has this giant screen about 60 yards from the 20-yard to the 20-yard, right? So it's equivalent to a 2,000-inch TV, right? So this TV, Jerry Jones can afford it. It's $100 million. You can't. We can't have it at the Turner, the local high school, and any other place. So for us to be able to afford such large screens or have this type of screens, but without a projector as a genuine high-resolution TV source, then we would need to make the pixels individually. So out of LEDs, you have to make 30 million pixels. 30 million LEDs needed to be produced individually. I got that information actually from the Coke bottles that they had at the AT&T Stadium released back in 2009. But they cost 1.5 million watt to operate these giant screens, and so we have huge energy saving, or as our current president called it, huge, right? So all of this can be saved because OLEDs require a very small fraction, less than 10%, to operate them and deliver the same light source. And the cost of producing OLEDs, you don't need to make 30 million LEDs. You can make them right now, the same technology that your professors here think used in their past. Didn't you use the overhead transparencies? So how did we print our lecture material on them? With inkjet printing. So inkjet printing is one of the common techniques to actually make these types of electronic devices like OLEDs and OTFPs, not just the light emitting element, also the transistor element and the rest of the device. So this is what these are some of the devices that we made. We also have an individual lab called Zero Energy Lab at UNT. And our football stadium is actually made by the same company that made the AT&T stadium, but it is actually green stadium. It's the only green stadium in the US. Okay, so I'm an inorganic chemist, so I talked to the companies that, okay, let's try to work together on improving the state of the art of OLEDs. Well, both them and DOE themselves raised George Bush's Mission Accomplished banner, right? They told me all the problems have been solved with the iridium phenylpyridine phosphors that are typically used in OLEDs. I told them not so fast. I told it to themselves. This slide here on the right is a presentation to the OLED stakeholders that DOE invited in a workshop, and maybe they made a mistake by inviting me there. So I told them, no, it is not time to raise the Mission Accomplished banner because we can still do better. So sustainability-wise, which people ignore, so everybody who makes OLEDs, high-efficiency OLED, including the green and red pixels in the Samsung Galaxy products, are based on iridium complexes. All the world records achieved in OLEDs are based on iridium complexes. Iridium, according to the government data in here, is the lowest abundant metal on Earth. So low I could reach it, right? Physically, without the laser pointer. So its origin is from meteorites. So you have to pray for shooting stars. We want to rely on iridium to solve all our problems in lighting in the future, right? So the maximum market penetration is like 6%. If we replace every incandescent lamp, every LED, every fluorescent lamp with an OLED, we cannot do that. If you use the entire world production, it will only give you 7% of these, 7% replacement of those. And iridium is used for catalysis, it's used for other things. So even if we go a step further, platinum or gold, so yeah, gold is expensive, platinum is expensive. They're used for jewelry, right? But they're actually 10 times more available on Earth, and gold is produced 1,000 times more, 3,000 tons versus 3 tons for iridium. So yeah, mission is not accomplished. We still need to do better. So let alone if we leave platinum and gold, and which is what we did initially, and go to something like copper or zinc or even metal-free systems. This scale is a large scale. You're going from the 10 to the negative fifth to 10 to the positive 3. So you're talking about, when I say sky's the limit, it's literal. We're talking about millions of times greater availability. There's a lot of problems that we can solve simply by doing that. So, and it's not just dreams, scientific dreaming. It gives you pleasure as a graduate student or an undergraduate student even, let alone a professor, that the companies are interested in it. So in that same all-stakeholder meeting, on our first day, they took us to a children's hospital where they use amber light based on LED. The next day, they replaced those LEDs with OLEDs. And the company that did that, they're talking to us to produce the 2.0 version of these amber OLEDs based on our materials and devices, which are a lot easier and a lot more sustainable than what they have. So we're talking about stuff that is industry related. And as you can see here from that picture, we can make these complexes very simple materials that can give you white light that achieves the standard that they're looking for. So with that, I will leave the floor to Claire so she can explain to us how to actually make some of these devices and optimize them. It's a little bit of some material science, but that is what she was trained to combine both chemistry and material science in my lab. Claire.
Thank you. So I really don't need to give you an introduction to this project since you got probably the most in-depth introduction, more in-depth than I could possibly ever give. So, there we go. I'm going to tell you what we were looking at for each type of devices that we were making, phosphorescent and fluorescent devices. So for our phosphorescent devices, and keep in mind that this includes our copper toner devices, which I'll get into a little bit later, so just remember that that's where those go. Of course, we're looking at optimum efficiency for obvious reasons. This includes high photoluminescent quantum yield, a balanced charge injection, and low drive or turn-on voltage. The lower turn-on voltage we have, the more efficient our devices are, which again, I'll kind of go into a little bit further in just a minute. We're looking for efficiency roll-off, triplet annihilation, triple flare-on annihilation, and field-induced quenching. Now, one of the differences between fluorescent and phosphorescent devices is that fluorescent devices utilize singlet excited states, whereas phosphorescent utilize singlet and triplet. So that's why you see triplet here and then singlet in just a second. We're also looking at the lifetime of our devices, the stability of our organic materials, as well as encapsulation. Now, encapsulation is where you just take your active site and you just kind of sandwich it with some glass to prevent oxygen from getting to it. And I'll actually show you probably one of the coolest pictures I've ever seen, but that's just my opinion. I'm actually explaining what that would prevent. We're also looking at the purity of color in these devices. So for fluorescent devices, again, we're looking at efficiency, low turn-on voltage, reduced efficiency roll-off, and whenever you get to the graphs, you'll actually see what I'm talking about when I say efficiency roll-off. So within that, we're looking again at our balanced charge injection, as well as reduced quenching. Now this is the singlet, single flare-on, and then again the field-induced quenching as with our phosphorescent devices. So then we get into the lifetime. Again, this is the same as our phosphorescent devices. We're not really changing that between the devices. And then again, color. Full maximum half width, which when you see a graph, I have a picture of it actually in the slides, but you're going to see a graph and it's just a little curve. We're talking about that space under the curve when I'm talking about full maximum half width. So you're probably wondering what the little CIE is. Well, that's this. It's our chromaticity diagram. Now this is the industry standard for color, because if we have a device and we're saying it's red, well, industry doesn't like that. They like us to have some quantifiable, for sure way that we could be like, oh, well, it's this color instead of just red. So each one of these little active sites are here. This is actually our OLED stack. This is where we get the colors that we're seeing, that we quantify over here. So each one of these little nodes right there is actually one of these stacks. Okay, there's kind of a little bit to unpack on this slide, so bear with me. But this is actually our OLED stack. This is what I was actually making all summer. So right here, we have our glass substrate. This is just regular glass. Then you have your ITO, which is your anode. Then you have your NPD, which is your hole transport layer. Then you have your ALQ3, which is your electron transport layer. Our electron transport layer actually has some hole transporting properties, thanks to this quinylanato group right here, which means that it's also our emissive layer, meaning that our holes and electrons actually recombine in this layer to give us the green light that we're looking at, because that's the color that our ALQ3 actually emits. So you have our lithium fluoride, which is our electron injection layer. Then we have our aluminum, that's our cathode. So when you apply voltage, you get charge movement, and you get charge recombination, then you have relaxation. And then you have the fluorescence or phosphorescence that you see. So where did I actually spend most of my summer? Well, I spent it in this lovely room right here. So this is our clean room at UNT. And this right here is a nitrogen-filled glove box, because our materials are actually very sensitive to oxygen and moisture. So in order to reduce the possible oxidation of our devices, we have to make them in a glove box. So within the glove box, you can see right there is this device. This is actually our deposition device. And so what we do is we put our materials right here, then they're thermally evaporated onto our substrates, and quartz crystal monitors right here in each corner tell us how much we're actually putting onto each substrate. So you can control what you're putting on each substrate, how much you're putting on each substrate by this right up here. And so what's right there, you have shutters, then you have your mask, and then you have your substrates. So what you can do is you can open and close various shutters, put it on different substrates, and you change out your mask depending on what it is you're actually putting on the substrate, depending on your cathode, which in our case is our aluminum, or your organic, which basically is everything else in our devices. So this is actually how we measure the devices. So we have our integrating sphere, which is actually where our sample goes. We put it right here. Then we have our multi-channel analyzer, or detector, our light source, our stepping motor controller, which just basically regulates the time taken between data points. And then we have just a standard laptop computer. So this is kind of what we were looking at for the research that I did. We're looking at turn-on voltage and power efficiency. So the lower the turn-on voltage, the higher the power efficiency. And then we are also looking at the quantum efficiencies, external and internal. So for external, it is the photons emitted from the surface, and then for internal, it's the photons emitted from your entire OLED stack that I showed you a picture of earlier. So these are the original overall structures that we worked with. These were actually pulled from some literature, but you can see that we're again using just the MPV ALQ3 that I took you through earlier. And so we're looking at neat, which is just, there's no doping involved, it's just 2 layers. This is the stack that I showed you is exactly what that is. Then we're looking at the single MPV doped, which is where you take 5% of ALQ3, dope it into our MPV, and then vice versa with our SAD, single ALQ3 doped. You take some of your ALQ3, dope it into your MPV. Then we have our double doped, and we did this to see which layers were more effective and which ones gave us better results depending on how we doped our devices. So these were actually the results. We got results while I was here doing research. I love it. So these are actually the graphs that we had. Again, right here, the lower the turn-on voltage, the better our power efficiency was, which is better for us. Right here, so what we're looking at right here is actually, we're trying to see like a nice steady state before we see our roll-off. That efficiency roll-off is what I was talking about earlier, whenever I was taking you through what we're looking at for each type of device. So you can see our double dope wasn't the most stable, but it did have the least amount of roll-off. And then again, right here, just note that our double dope was in fact better. There at the very end, you can see. And then right here, kind of a funky looking graph, but basically everything before 1 doesn't apply to these graphs because this is actually before we hit turn-on voltage. And again, just for our luminance, it's just nice to see how bright our actual devices get, how bright each pixel can get. So then, we just took all that, all the data, put it in a table. I bolded the ones because I like to see which data works best. We found that our double dope worked best to set up our single dopes for our bilayer, which was kind of expected. So we decided to take it and run. Then we got into other kinds of doping. So we got into graded and mixed. So what this does is this actually expands our emissive layer, and this reduces the charge barriers that the electron and holes would have to overcome in order to recombine. So here again, just the same graphs that we had earlier for the other devices. Lower turn-on voltage, better for us, happier everyone. And in this one, everyone had a very nice steady state before they rolled off, which is exactly what we want to see. And again, our graded average actually was the best, which is a pretty interesting point. And again, just a nice steady state. This is our EQE. And our luminance and our graded average basically beat the snot out of everybody else in our terms of our devices. So then I took this again and I put it in the table, bolded the ones I liked, and I like red, so I put them in red. So then we see that our graded actually had a better turn-on voltage, whereas our mixed devices had better luminance and power efficiency peaks. It's kind of expected because we expected our other devices in terms of other dopings and other gradients and other things like that to have better results than our double doped and of course our bilayer that we kept as a control. So that was fluorescent devices. Now we're into phosphorescent devices. So we worked with PTA primarily, and this is a novel material. This hasn't been used in OLED before, so all of this testing was brand new. It was very exciting. This is a tunable material, meaning that we can change the color of this depending on the concentration that's in the devices that we're putting in. Solvents, temperature, things like that can actually affect the color. The last I heard, there's actually a new PT complex that had been found. It was being synthesized. I'm not sure what else has been happening with that, but I thought that was very cool. This right here is actually the graph that I mentioned earlier where you could see the full maximum half width. This again is a good industry way for us to tell them what color it is we're actually producing with our devices. A little active pixel right there. I don't know, but that's great to see anytime you're doing research like this, so I was very happy about that. So this, I think, is my favorite slide in the entire presentation because this actually shows you what it is we're trying to prevent. So this right here, we actually added x-axis error bars to show you how the roll-off is affected. You can see right here, before the roll-off happens, we have a pristine surface. This is taken with SEM, scanning electron microscopes. We have a pristine surface, which is this is what we like to see. And then after we hit the roll-off, we actually see this. Now, I don't know if you can tell, but those are little pock marks. Those are little pits of corrosion. And so what happens is when you have a charge applied to your OLED, it opens up the surface of your OLED, oxidizing it and actually kills your device. This is called oxidation. So I thought that was very cool to see actually what it is we're trying to reduce in our devices. I don't know about y'all, but I was excited. So these are the devices. We did a bilayer. The TAP-C is our whole transport layer for this device. This is a material that has been used before. And again, we have just the same devices, still standard bilayer. which we wanted to use as just like a baseline. This is kind of our control before we get into further devices. And we'll be using the structures that we actually looked at in our fluorescent devices. Those were also training devices to kind of help us figure out which structures perform best in order for us to kind of utilize them in these devices. You can see that the efficiency reduced after 8 volts because these bars actually got bigger. Again, average current efficiencies. I don't know, like I said, I don't know about y'all, this is really exciting because this is all novel research, this is all novel materials. So we had average power efficiency. Again, same graphs that we had for our other devices. So then we got into the copper trimer emitter. This is kind of my baby over the summer. So what we did was we took a solar cell, and so solar cells, if you know anything about them, have an emitter. In this case, we had a copper trimer emitter. And so we took that emitter and we were like, okay, well, we're going to try and test it in OLEDs. So this is the synthesis procedure. We have just using standard shrink techniques, which I had to learn, and using benzene, a chemical. This is just the layout of the synthesis and what happens. And right here is our little product. You can see it's white. And when we put it under UV light, we actually get a really pretty orange color, which I thought was cool. So basically, after running lots of tests on our copper, this is what we found out. We found out that we could use it, most likely, in our devices, because it would reduce the cost, as Dr. Omary talked about quite extensively. Copper is a cheaper and more abundant metal than, say, iridium or platinum. It's a very stable material. We actually successfully vacuum deposited this material in our deposition device onto substrate, so we know it's a very stable material. It has a high quantum yield. We found literature that recommends 77% for this material. It's relatively short lifetime and is stable in air. It's more stable in air than the materials that we have been working with. Now we found it to be used as a dopant rather than a full layer, which means it would be doped into a host. Because similar copper complexes that we found in literature have been used as dopants, and then we need to conduct more measurements of this material. So, first one was to get photophysical properties of copper trimer. We needed to take several more measurements using several more devices. I don't know if actually happened yet because I'm getting gone. And then we need to test the PCA complexes further because those were pretty promising actually. Then we need to develop our optimal structures for the phosphorus devices. Again, like I said, using the structures that we found in our fluorescent devices that work the best. And then we need to develop new platinum-based phosphorescent materials for solar cells and OLEDs. And there's me actually doing work to prove that I was there and doing things. And yes. So acknowledgements, Dr. Omary, and thank you very much. And I'll hand it back to Dr. Omary.
Thank you. Good job. She has magic hands because the laser pointer wasn't working with me. Okay, so she touched on solar cells. So this is our second element or second app, right? So for solar energy covers the entire visible region, and actually more than 50% of solar light is in the near infrared region. So so the near infrared from about 700 and longer. So the area under the curve is greater for that. So we need something that covers the entire visible and intrude into as much as possible into the near IR. Problem is that normal organic semiconductors used in the technology, like this polymer here is called poly-3-hexylthiophene, P3HT. It overlaps pretty good with the peak of the solar radiation, but as you can see here, there is a gap in the shorter wavelength and a huge gap in the visible beyond the green region, and nothing in the near IR. This copper phthalocyanin, another well-known material, it's more like a charge transporter in electronic devices. It does better at longer wavelengths, so it covers the gap in the red, but at the expense of the peak. So there's a hole here in the green and blue region, picks up in the UV. What we want, the beautiful material here, is a black absorber, absorbs everything in the visible, and that's what we're able to synthesize by this binary material. It's, again, we start with something expensive, do the device fabrication with first, and then we go to something cheaper. So this is a platinum complex. We're not quite anti-organic. We do some research on organic molecule. So this organic molecule, electron acceptor, actually improves the performance of this platinum complex. So it makes it absorb in the near IR where neither the platinum complex or the organic acceptor absorb by themselves. So you can see here it overlaps with the entire visible and a good portion of the sunlight up to 1200 nanometers. It actually does better than silicon. Silicon solar cells, which are the prevalent right now, their band gap is about 900 nanometer. This is 1200 nanometer, as you can see here. And we're not just talking theory, these are actual devices. So you can see here in the dark, there's no current produced, but if you drive it with either UV or visible photon, it absorbs, it generates electricity, generates current here. So if you follow the current versus wavelength, it is constant from 220 to about 720, because again, it absorbs everything in that region. So this is something in action. In terms of material design to go cheaper, that's where we go next. So we look at nature for inspiration. These beautiful colors of vegetables. All of that is simply conjugation of something that's a chromophore that's only a UV absorber, ethylene. So the ethylene group by itself, if you look at ethylene in the gas phase, its UV vis is of like 175 nanometer. But if you have diethylene, triethylene, tetra, so forth, up to 11 you get carrots. You get beta-carotene. So beta-carotene has 11 ethylene groups conjugated to each other. 13 you get tomatoes, and more you get black color, which is like eggplant, etc. Right? Well, that sounds good, but in terms of devices, you cannot use vegetables. Yes, you can use it for proof of concept, but it will last about, the device will last about 3 seconds. So, because there's with organic molecules, photobleaching is a major problem. So what we do is that we use the same principle. We just look for these different organic ligands. The greater the conjugation, the greater the number. Instead of 11, we have even smaller, but we connect each of them with a copper atom, copper 1 atom, and copper 1, by the way, absorbs only in the UV. It's D10, it says D10 electron configuration, so there is no DD transitions, which gives the color for metal complexes. But the individual copper ions are conjugated with things like bipyridine here, infinitely. So we don't need 11, 13, we can have infinity, right? So when we have infinity, then we have these different colors and produce high efficiency that covers the entire visible region. These are the actual pictures of these metal complexes that we made with these different organic linkers just being bonded to copper 1 ion. So neither the organic linker nor the copper ion absorb in the visible, yet the combination gives you these metal organic frameworks and coordination polymers that absorb in the entire visible region. So that is how we look at it. The third app is energy storage. So for energy storage, you need to store gas molecules in the solid phase. So you need to make molecular sponges. So molecular sponges are coordination polymers, the way we define them. They're called MOF, metal organic frameworks. Okay, so this is one example of a MOF. We call it fluorinated MOF, fluorous MOF. So there's no hydrogens at all. So it's a silver coordination polymer. So this MOF absorbs toluene molecules. This FMOF2 version has toluene molecules not only in the main channels, even in the smaller nano cages around them. So doubles the toluene uptake from 2 to 4 per unit cell. Well, as you can see here, it absorbs no water. So CNE News picked up this paper that we published in JACT in 2011, and at the time it was fresh off of the Deepwater Horizon oil spill in the Gulf of Mexico, right? So as you can see here, water doesn't get absorbed at all in this material, whereas oil is welcome to the pores of these MOFs. So that is liquid gasoline for oil spill, but for gas phase, natural gas, which I started in the introduction saying that we're very rich at. Basically, you can empty the content of an entire gas tanker in a small cylinder if you have enough amount of this porous material in gas cylinder that contains our MOF, our fluorinated MOF. So, nothing does better than this. We have the experiments done in methane. Nothing does better in terms of resisting water than this material, because if you look at other conventional materials like zeolite, which are hydrophilic, they saturate at 5% humidity. Activated carbons like BPL, that's supposed to be hydrophobic, just carbon, right? They resist humidity only up to 40%. More than 40%, it picks up, even becomes worse than zeolite. There's a lot of, yes, the activated carbon is supposed to be just pure carbon. You burn off everything else in the organic material, in the biomass, usually from trees like, one of my mechanical engineering colleagues, he goes to the, and looks at, plants that are in abundance in Texas, like kenaf trees. He's Chinese, in China, they have an abundance of bamboo trees. So he burns those to death. That's pyrolysis, 1500 degrees or more, and that produces activated carbon. It's supposed to kill all the nitrogen, the oxygen, the sulfur, everything else. Theoretically it does, but experimentally, as you can see, there it still has some oxygen groups, some aldehydes, ketones, alcohols, acid groups, and on the surface, even small amounts, but still accumulates large enough. That is even in the humidity, in the gas phase. And real water, if you're in contact with real water, we have humid days, and even in North Texas, that's more than 80% humidity. Whereas our materials, actually, we can soak it in liquid water for a week, for a month, take it out, there's absolutely no water in the pores. They're pristine as the porous material crystal structure has. So that takes us to the environmental apps. So I already mentioned the oil spill, carbon capture, CO2, they do well for the CO2. Toxic industrial chemical, we've been fun, and warfare reagents, filtration, so we want our soldiers or citizens to be protected from chemical weapons attacks, from things like chlorine gas, which Assad poisoned his citizens with, things like that. So we, unfortunately, water is in the atmosphere and does compete for the active sites of these porous materials. So our FMOFs are very useful for those as well. Anyway, there's so many different applications for that. One of them that, yes, the good thing about natural gas, the oil companies will tell you it's great because it saves 50% versus liquid gasoline in terms of carbon production, CO2 emissions that contribute to climate change, global warming, etc., right? So we should support natural gas. But it's the expense of our water. So, the fracking process pumps millions of gallons of water, sometimes competes for our seawater, for our drinking water, and it actually reaches the water reservoirs that we drink from. So up to a mile from the fracking sites, people found evidence of the fracking fluid and other materials. So since our material is super hydrophobic, as you see, my students actually had the smart idea of making basically a tea bag out of this porous material. So we started from the fracking produced water. Produced water, basically, that is, after the fracking fluid goes down and the site gets the natural gas. The natural gas is taken away, packed and everything. There's still enough traces of gasoline and fracking fluid in the water. They skim off the surface, but there's a lot of surfactants that will mix with the water. So even the produced water is supposed to be purified. All the crop is taken. It's still extremely, and we try to do extraction. Like Naive, they said, to my students, let's just do extraction to get rid of a lot of it, and then just purify the rest. And that didn't work with her. So we still had to deal with this sample here. If you look at the UV vis spectra that shows the hydrocarbon area, so you see the hydrocarbon in the original fracking produced water here. We dilute it enough so we can measure it on the UV vis. We add that, in a small column that we make just from my TAMS student, actually. We have the TAMS program, high school students. Spend the last 2 years of high school at UNT. We select 200 smart kids every year for that. So he had this idea of using dispatcher pipette just puts cotton swabs in the bottom and top, around the solid porous material. So we wanted to look at standard porous material, so we started with zeolite. You can see zeolite is hydrophilic, so the reduction was very minimal. Activated carbon, BPL, hydrophobic, did a little bit better. Look at the FMOF, or FMF, we changed the name to metal inorganic frameworks because the linkers are actually inorganic complexes. It's whole gone, it's entirely gone. And the picture says better than 1,000 words. The other thing is that in the nasty fracking liquid, there is other chemicals like some toxic elements like silver, mercury, lead. We heard in the last election around about the lead in Michigan, right? Actually, we have in Georgetown, Texas, we had more than Flint, Michigan. But anyways, as you can see here, we have part per billion amounts of silver, at least, being detected by this metal complex that we use, this red-emitting gold complex. We add part per billion quantities of silver. It changes color to green from red. And whereas, another composition, if we look at other toxic metals like mercury, lead, thallium, it detects it, but in the part per million levels. And we're changing the chemical structure of the sensor to be more selective to lead and mercury, etc. There's also nuclear waste. There's so many different things, not just organic, inorganic, and other types of materials. Okay, last but not least, biomedical apps. So that's where the nano world comes. So we produce metal nanoparticles for cancer therapy and detection. So, beauty beyond jewelry. So gold is beautiful for its, jewelry for the ladies, right? But what we do is that we actually dissolve it to make liquid gold by dissolving it in aqua regia. And then that produces trichloroauric acid. Then we make it stinky gold, gold 1 complexes. That's, it's a white emitting, it's a white colored complex, right? It's the +1 oxidation state, gold is D10, there's no color again. And then what we do is that we usually add a chromophoric ligand to make the type of phosphor I showed you earlier in the picture. But the student one time left it alone before adding the ligand that makes it luminescent. And the next day, instead of having the colorless liquids, he found all of these beautiful colors, and that's because that is the gold in the nanoscale. If gold aggregates with itself but stays in the nanoscale, it gives you these different colors. And the beauty is that the near IR emitting particles like rods and prisms, to make them, you typically have to add some toxic surfactants like cetyl trimethyl ammonium bromide, CTAB. CTAB, as you can see here, is just like the controlled Triton X cell killer. It kills all the cells. Whereas our particles prepared this way, they only contain edible ingredients here, right? So the byproduct is dimethyl sulfide, which is what makes cabbage stink. And the stabilizer that keeps gold in the nanoscale is chitosan, which is derived from shrimp, right? We also have a chocolate-flavored gold nanoparticle with lecithin being the stabilizer. Okay, so as you can see here, without any dilution in the assay, our nanoparticles are benign completely. So they will not kill the healthy cell. They will only kill the cancer cells. And you can see that these are the healthy cells. If you irradiate them with amber light, they're busted up. And you can see here them being killed gradually. So that's all. I just wanted to end with a summary that all of these applications or apps are enabled by smart science. So the type of thing that we have is discovering new chemical bonds. You could be famous, so a bond would be named after you. These are the two students that worked on discovering this bond by experiment and theory. And my hypothesis is that you need two different metals to form this gold, D10 bond. But they found that if there's different donor atoms in the ligand, even the same metal can produce this bond. So, but these are the materials that produce the high quantum yield, efficiency, etc. But that is basically the take-home message. And in the end, I would like to thank you all for your attention, and all my students. And yeah, there's a few slides here that I wanted to tell a story, but there's no time. Yeah. So those were from a classroom project in the inorganic teaching lab, but I did want to end with the acknowledgement of the Army, of the graduate students, postdocs, and undergraduate, including Claire, who worked with us in the lab last summer. So these are different pictures in our group since 2001. We garnered more than 200 students. And this is the last picture with Claire and the IEU program poster. Thank you all again.
Well, Dr. Omary will be here if you have questions. Otherwise, we'll see you all next week.
I honestly don't understand any, if all of it.
Well, then you've got time to ask questions.